All right, now let's actually talk about the second half of Investigation 4, which deals with heating and cooling degree days. So imagine that you're a meteorologist working for PG&E, and I actually have several colleagues who actually work there, and in fact, if you've ever heard of Allison Bagley or Scott Strenfield on the radio, they actually are PG&E meteorologists, and let's assume you're not worried about your job right now because of the whole fires and everything like that. Sorry if you work for PG&E. One of the things that meteorologists are really important for in a place like PG&E is helping plan energy needs. And in order for them to do that, they've actually created their own index that they can use to identify, okay, how much gas do we need for heating, how much electricity do we need for cooling, and so on. And so this gave birth to what are called heating and cooling degree days. And these are what are talked about here in Investigation 4B. So the way that it works is, first, every day there's a high temperature and a low temperature. If you ever open up your phone and look at the weather app, they give you a high temperature and a low temperature. Well, what energy forecasters do is they actually calculate the average of those two numbers. So the average of the high temperature and the average of the low temperature. And then that number is then used to determine heating or cooling degree days. And so I wrote here an example of this. Let's say your location has a high of 80 and a low of 50. If you take the average, that gives you a temperature of 65. Now, actually, 65 is a pretty unique number because the whole heating and cooling degree days is based entirely off of 65 degrees. And here's how it works. Whenever the average temperature is below 65, that means that it's cool enough to where people are going to be turning on their heaters. They're going to need energy for heating. And so the way that heating degree days work is 1 degree of heating in a given day. And the way that it works is that for every degree you're below 65, you accumulate 1 heating degree day per degree below 65. So let me give you an example. Let's say you have an average temperature of, let's say you have an average temperature of 60. Well, to determine heating degree days, you figure out what the difference is between 65 and 60. You can actually just subtract, so 65 minus 60, that gives us 5 heating degree days. And so on that particular day, we need enough energy to heat houses by 5 degrees. And so that's how heating degree days work. And you'll see a few examples in this lab manual that'll actually walk you through it, but that's really how it works. So for every degree below 65, you add a heating degree day. So if the temperature was 35, that'd be 30 heating degree days. Or if the temperature was 45, that'd be 20 heating degree days. Now, on the other hand, if the average temperature is above 65, then it becomes warm enough to where rather than turning on the heater, people are likely going to be turning on the air conditioner. And that results in what are called cooling degree days. But the same idea works with heating degree days. 1 cooling degree day is 1 degree above 65 Fahrenheit. So let's say the temperature was, and I'll give you a more abstract one. Let's say not abstract, but a little more complicated. Let's say the temperature is 73. So the average temperature for the day is 73. Well, to determine how many cooling degree days, subtract 65, and that gives you 8 cooling degree days. That gives you 8 cooling degree days. And so that's how you do this. You're just looking for the difference between that day's temperature, that day's average temperature, and 65. If it's higher than 65, then that is a cooling degree day. If it's lower than 65, that is a heating degree day. Now, with that said, the very next thing that they show you is a map, and then they want you to draw ISO lines for this. And I took a look at this map, and not to criticize AMS or their textbook, but I banged my head against the wall. And when I tried drawing this map, it was frustrating, and then the very next thing, they did it for us. They actually did it for us. So here's what I'm going to say. Don't worry about drawing an isoline map for heating degree days. Don't worry about it. Instead, you already have one in this figure right here. So this figure is going to be good for referencing. In fact, they're going to have you compare San Francisco, which, yeah, let me get my little cursor here, which is right here, to St. Louis. And they're going to have you actually compare the two cities. And if you take a look, San Francisco has a lower number of total heating degree days. St. Louis has a higher number. What they actually want you to be able to do here, let me get rid of that ink now. What they actually want you to be able to do here is just identify what pattern primarily applies for the United States with heating degree days. And let me walk you through it. If you notice, lower latitudes typically have lower heating degree days. I mean, look at cities like South Florida, so Miami, so down here in Miami, or over here in southern Texas, like the city of Brownsville. You notice that those cities accumulate less than 1,000 heating degree days per year. However, as you travel north in latitude, so now as latitude increases, look what happens to the number of heating degree days accumulated per year. It almost exclusively goes up. Now, with that said, if you take a look here in the West Coast, you notice you don't get that same nice, almost evenly spaced row pattern, and that's because we have a bunch of mountains here on the West Coast. So we have the Sierra Nevada, we have the Central Valley, we have the Rocky Mountains. And in fact, you see that slightly, let me grab my cursor again. There it is. Sorry about that. You actually have that slightly over here on the eastern part as well. This is actually the Appalachian Mountains. But again, the dominant pattern I want you to see is that as you travel north, as your latitude, your distance from the equator increases, the overall number of heating degree days you need also seems to increase. Now the last thing, or the last two things that they have you do on this are compare San Francisco to St. Louis, and they're going to ask you two questions here. And the two questions are this. First, which of these two cities has more months that accumulate heating degree days? And the way to do that is look at each city and count how many dots, these represent the average temperature for each month, how many dots are below the 65 degree line. Again, I can't give you an answer. You're going to have to come up with it yourself, but you'll be surprised at the answer. One of these cities is always below the 65 degree line. The other city peaks above it a little bit. And then the other question that they ask you is, okay, so which city accumulates more overall? So which city has more months that accumulate them, and then which cities accumulate them overall? And go through the lab, take a look at it, see what you find, and if you have any questions, please don't hesitate to reach out to me. Now, the very last thing that they're going to talk about is what's called the WET, or the wind chill equivalent temperature. So I'm sure that you know, if you've ever been outside on a windy day, it typically feels colder than it would otherwise be. Well, believe it or not, the temperature itself is actually not colder, but the nice warm layer of air right around your body is colder. Or it's blown away. Sorry, let me rephrase that. It's blown away. So that nice warm layer of air around your body that keeps you warm gets blown away. And that makes the temperature feel way colder than it otherwise would be. Well, the National Weather Service has actually come up with a pretty good way of relating wind speed to how the air temperature feels. And it's using this chart right here. And to figure this out, you would then get what's called the wind chill equivalent temperature. So let's say the temperature outside is 15 degrees. And let's say the wind outside is 20 miles per hour. To find the wind chill equivalent temperature, to find that wet, what I recommend doing is starting at 15 and then traveling down until you intersect. So I said a temperature of 15 and a wind speed of 15. And look where the two intersect. Or I think I actually said 15 and 25. Sorry, I'm getting old. My amnesia's setting in. Let's actually scroll down a little bit further, and voila. But wherever the two lines intersect, that's your temperature, or that's your wind chill equivalent temperature. That's your wet. So for example, with a temperature of 15 and a wind speed of 15, your wet is 0. Or for a temperature of 15 and a wind speed of 25, your wet is -4. Now, one of the interesting things that they point out is that when you go from calm to slightly faster winds, you notice a big decrease in wind chill equivalent temperature. But actually, the faster the wind blows, the smaller that decrease is going to be incrementally. So, for example, let's take a look at 0 degrees, and let's look at 0 and 20 miles an hour. So from 0 to 20 miles an hour, you notice a 22 degree temperature drop. Now, if we were to actually up at another 20 miles an hour, so it's now like at 40, you only see 7 degrees cooler in that case. So the initial bump was 22 degrees lower, doing the exact same bump, so an additional 20 miles per hour, only results in an additional 7 degrees of cooling. So the faster the wind becomes, the smaller and smaller the difference from a slightly slower wind to that new faster wind. So that's it for Investigation 4B. In Investigation 5, we're going to talk about air pressure, height, and also talking about frontal passages, some stuff that I really love talking about. And I'll talk to you about that then. So if you have any questions, as I always really want to stress, please don't hesitate to reach out to me. Please come to my office hours, send me an email, send me a Canvas message. Any way that you need to get a hold of me, please don't hesitate. I know these labs can be tough sometimes, and I just want to be here to help. All right, so that's that, and thank you so much for watching.